Look at this line cutting through a three-dimensional grid. A continuous, straight line is the strict geometric foundation driving action across digital and physical engineering. In aerospace engineering, this precise geometry dictates a spacecraft's orbital burn. The thruster's output dictates a straight, linear path through the void. In telecommunications, 5G phased array antennas rely on the identical geometric principles to emit tightly focused, directional signal beams toward specific hardware receivers. And in computing, modern rendering engines construct entire visual worlds by treating this geometry as virtual light rays, cast outward from a digital camera into a simulated scene. Whether it is a rocket trajectory, a radar beam, or a ray trace, these disparate systems are solving the exact same geometric equation. To define a line in 3 dimensions, you need 2 strict parameters. First, it must possess a fixed position vector. This acts as the specific origin or anchor point in space. Second, it must possess a definitive orientation that locks its trajectory, telling it exactly where to go from that anchor. Visualizing these continuous lines as vectors in space is intuitive for human spatial reasoning, but computer processors do not map continuous geometric vectors natively. To command these systems, engineers have to translate that continuous geometric trajectory into discrete, programmable algebraic coordinates. Mastering this translation, converting back and forth between vector geometry and Cartesian math, is what allows the logic of 3D geometry to function within the constraints of a digital processor. This 3D Cartesian system shows a single line passing perfectly through the origin. We define its orientation by the distinct angles it makes with the x, y, and z axes, alpha, beta, and gamma. Taking their cosines gives us the direction cosines, L, M, and N. But there is a bottleneck here. Constantly calculating floating point cosine values takes heavy processing power, and it introduces tiny imprecisions during rapid intersection checks. The programmatic solution is a concept called direction ratios, represented by variables a, b, and c. They are numbers proportional to the direction cosines. Multiplying our cosines by a scalar value, k, gives a highly efficient mathematical shortcut. By scaling these up to whole integer direction ratios, a computer can perfectly orient a line in 3D space without ever running a single trigonometric function. We have successfully digitized a line's orientation. We turned angles into direction ratios, giving us a format that a processor can handle natively. We can apply those direction ratios back to the aerospace scenario to map a linear burn path for an orbiting spacecraft. This diagram illustrates a 3D grid where position vector A maps the spacecraft's current coordinate. A second vector, B, represents the thrust, containing the exact A, B, and C direction ratios to establish engine burn orientation. Any future coordinate the spacecraft will reach along that thrust path is our target point, labeled vector R. This gives us the full vector equation, R equals A plus lambda B. It is just vector addition. The lambda variable is a scalar multiplier representing physical distance traveled, or elapsed burn time. Changing the value of lambda physically slides that target point forward and backward along the continuous line. This specific mathematical framework is perfectly optimized for generating continuous paths and shooting rays outward into space. However, checking if a specific foreign object lies on this trajectory requires solving the vector format for an unknown lambda across all 3 components simultaneously. To make that check more efficient for a computer, we translate the single vector equation into its constituent scalar parts. Think of a modern radar array trying to confirm if a specific drone receiver is sitting inside its signal beam. Checking an exact 3D coordinate requires expanding the vector equation. We break the vectors down into their I, j, and k unit components, representing x, y, and z, exposing exactly how the axes behave independently. Next, we isolate all the x components into one column, the y components into a second, and the z components into a third. By equating the coefficients across these groups, we completely isolate the scalar multiplier, lambda. This yields the final Cartesian proportion. You can see how lambda acts as the strict mathematical anchor connecting all 3 spatial dimensions equally. We can apply this Cartesian format directly back to our radar intersection problem. To test the collision, the drone's spatial position is plugged into the x, y, and z variables, while the radar's origin serves as x1, y1, and z1. The system then calculates the fractional ratio for all 3 dimensions simultaneously. If all 3 fractions evaluate to the exact same constant value, meaning they equal the identical lambda, a collision is mathematically confirmed. If even one dimension varies, the drone is off the path. Isolating lambda structurally transforms a path generation tool into a high-speed algebraic collision detection tool. In modern computing, software processes this exact mathematical translation instantly. Programmers rely on symbolic algebra libraries, specifically SymPy in Python, which parse and translate between vector and Cartesian formats natively. Here is a computational workspace demonstrating this in real time. On the left is an abstracted Python script using SymPy variables. On the right is a 3D matplot graph rendering the corresponding line. The first variable we can simulate is altering the starting position vector, the x1, y1, and z1, directly in the code. Changing these anchor coordinates instantly translates the entire line's starting point to a new location in the 3D plot. The second simulation variable is altering the direction ratios, a, b, and c. Changing the ratios immediately updates the denominators in the Cartesian math. The line in the 3D graph physically pivots, adopting an entirely new trajectory. Vector geometry and Cartesian algebra represent the identical physical behavior, simply viewed through different operational lenses. Mastering the translation between defining a path geometrically and verifying it algebraically is how engineers align the physical reality of orbital trajectories and signal arrays with the mathematical logic of the engines that control them.